So imagine you build this massive wall, right? You dig a deep moat and you pull up the drawbridge.
Yeah, the classic fortress approach.
Exactly. And for decades, that was basically the foundational strategy for enterprise cybersecurity. Like, you authenticate at the front gate, and the system just sort of assumes that, well, anything inside those walls is safe.
Right, which was fine when everyone was actually inside the walls.
But what happens when that castle when it disappears entirely? What happens when your living room or an airport lounge or a random public coffee shop is suddenly the front line of a cyber war?
Well, you're forced to completely re-architect how you approach defense.
Right.
Because when that traditional network perimeter vanishes, the only logical step is to push the security directly onto the endpoints themselves.
You have to adapt the enforcement layer so it travels with the data.
Exactly.
So on that note, you are listening to the WeCyberYou Unlocked podcast, and we are really glad you're joining us for this deep dive.
Yeah, welcome.
Today, our mission is to unpack the mechanics of this source material we have, the complete enterprise guide to host-based firewalls.
It's a great guide.
It really is. We're looking at the technical realities of how individual devices defend themselves dynamically in a world where network borders just simply don't exist anymore.
Right. And to understand why the host-based firewall, or HBF, as we'll probably call it.
Yeah, HBF is easier to say.
Right. To understand why it's become the ultimate local defense, we first have to look at the mechanical failure of that old perimeter model we just mentioned.
The castle and moat.
Exactly. Historically, if you were an employee sitting at a desk plugged into a corporate Ethernet switch, there was this massive hardware firewall sitting at the edge of the network protecting you.
Monitoring all the traffic coming in from the internet.
Yeah, the north-south traffic.
But attackers, they evolved. They realized that they don't actually need to batter down the front gate of that network firewall.
Right, they just bypass it entirely.
Yeah, they compromise a single low-value asset, like a smart thermostat, or maybe a receptionist's mobile device, or just a laptop connected to a home network.
Something with a weaker defense.
Exactly. And once they establish that initial foothold, they no longer have to cross the network perimeter. They're already inside.
And that's where the concept of lateral movement comes into play.
Right.
Because once an attacker is inside the environment, they shift their focus to east-west traffic.
Moving sideways.
Moving sideways from device to device. They scrape memory for authentication tokens. They attempt to pass the hash to gain higher credentials. And they just quietly map the internal network.
And the traditional edge firewall doesn't see any of this, right?
It's completely blind to it. Because the traffic never actually leaves the internal switch. The attacker is just hopping between trusted machines.
It's kind of like, well, let's compare it to a bouncer at the front door of a nightclub.
Okay, I like that.
The bouncer works perfectly fine, right?
Yeah.
Checking IDs, keeping bad actors out. But it only works until someone sneaks through a back window in the bathroom.
And then the bouncer has no idea they're in the club.
Exactly. So the host-based firewall is less like a bouncer at the door and more like a personal, highly trained bodyguard assigned to every single guest inside the club.
Protecting them no matter where they wander inside the building.
Yeah.
That's a really good analogy. And that establishes the critical requirement here. We aren't talking about a piece of hardware anymore.
Right, it's software.
It's a software security mechanism running directly inside the operating system of the endpoint itself.
Whether that's your laptop, a physical server, or even a virtualized cloud workload.
Exactly. It enforces network policies at the local network stack level. So no matter where your device physically travels, that enforcement engine stays active.
Evaluating every single connection attempt.
Evaluating everything before it ever reaches the application layer.
So if we zoom in on, say, a single data packet hitting your laptop, the source guide outlines this really fascinating 4-stage gauntlet. It has to run in just a fraction of a millisecond.
It happens incredibly fast.
So the first stage is packet arrival.
Right. The network interface card receives the electrical signals, converts them to data frames, and passes them up the OSI model to the operating system's kernel space.
And that initiates stage 2, which is rule matching.
Yeah, and this isn't just looking at the source and destination IP addresses.
It's way more complex than that.
Much more. The firewall evaluates this complex matrix of criteria. It looks at the specific port being requested, the protocol being used, like TCP, UDP, or ICMP.
And it heavily relies on application-based rules, too, doesn't it?
It does. It has the capability to verify that the executable requesting network access is legitimately, say, Microsoft Teams.
Right, and not some unauthorized background process trying to establish a command and control connection.
Exactly. And it goes even deeper with user-based and time-based rules.
Oh, right. So the local firewall can query the operating system to see which specific user account initiated the process.
Yeah, so a standard user might be blocked from opening a remote shell, whereas an authenticated administrator might be allowed to do it.
And time-based rules.
Those further restrict access by ensuring, for example, that a database server only accepts remote maintenance connections during a very specific overnight window.
So if a packet comes in outside of that window,
It's silently dropped.
wow. Okay, so that level of granularity is highly effective, but I want to challenge one specific framework mentioned in the source material.
Okay, go for it.
It's the location-based rules and profiles.
Right.
The guide breaks down how a host shifts between a domain profile on a corporate network, a private profile on a trusted home network, and a highly restrictive public profile for, like, open Wi-Fi.
Yeah, the three main profiles.
But if my machine is constantly changing its behavior based on whether it detects the corporate DNS server or a random airport gateway, aren't we just recreating the concept of a perimeter? Just a smaller, individualized one?
Well, I mean, it's an understandable comparison, but it is fundamentally different.
How so?
Because it's not about geographical boundaries anymore. It's about context-aware computing.
Okay.
The endpoint is utilizing network location awareness. It looks at the default gateway MSC address, the DNS suffixes, the available domain controllers.
It's profiling the environment itself.
Exactly.
Oh.
When you are plugged into the corporate office, it verifies that highly monitored context and allows IT management tools to communicate with your device.
But the second you open that same laptop at an airport terminal,
It analyzes the new gateway, realizes it can't authenticate the environment, and instantly shifts to the public profile.
and that shuts down inbound management ports.
Yeah, because it operates under the assumption that every other device on that open Wi-Fi is potentially hostile.
Which proves how adaptable this software really is.
Right, it's shifting from topological trust to zero trust dynamically.
So for you listening, if you've ever tried to, remote into your desktop from an airport lounge and your company VPN stubbornly refused to connect, this location-based public profile is exactly what was happening behind the scenes.
Your machine's local firewall basically evaluated the network context, decided the connection attempt was anomalous for a public setting.
And just drop the traffic to protect your device.
Exactly. Now, because we can define these granular rules and profiles, the firewall actually has to enforce them constantly.
Which introduces a secondary problem, right?
Yeah.
Efficiency.
Right.
Because I imagine tracking every single packet and evaluating it against an exhaustive list of application and location rules would just absolutely cripple a machine's CPU.
It would. And early firewalls were stateless, meaning they inspected individual packets blindly against an access control list without any context of the broader conversation.
So I'm assuming modern host-based systems have to use stateful inspection to keep memory and CPU usage manageable.
Yeah, that's the core architectural difference. A stateless approach is incredibly inefficient.
Because if you stream a video or download a large file, the computer receives millions of packets.
Millions. And a stateless firewall evaluates every single one of those packets from scratch.
Wow.
But stateful inspection changes the paradigm. It monitors the actual state of the connection in active memory. It specifically tracks the TCP handshake.
Right, the SYN, ACK, and ACK sequence.
Exactly. So when your computer sends out that initial SYN packet to request a secure HTTPS connection with a banking server, the firewall logs that initiation in its active state table.
Okay, so it remembers that you asked for it.
Right. And when the banking server replies with a SYN ACK packet, the host-based firewall checks its state table, sees that the internal machine explicitly initiated this exact conversation, and dynamically allows the return traffic through.
So it validates the traffic flow without having to run a full resource-heavy rule evaluation on every subsequent packet.
You got it. It understands the context of the session.
It's kind of like, it's like being at an exclusive event. If you personally invite a vendor inside to speak with you, which is like initiating the session,
Right.
the security guards automatically know to let them answer you. They don't make you sign a new permission slip for every single sentence the vendor speaks back to you.
That's exactly how stateful inspection works.
But that handles the connection state. It doesn't actually solve the problem of what is inside those packets.
No, it doesn't.
Because it's entirely possible to establish a perfectly valid stateful TCP handshake with a server that is, secretly sending you malicious commands wrapped in standard web traffic.
Which brings us to deep packet inspection, or DPI.
Right.
Standard stateful inspection only looks at the headers. The source, destination, and ports. It doesn't look at the payload itself.
But DPI does.
Yes, DPI acts as a highly advanced real-time pattern matcher.
So it is actively disassembling the payload as it arrives in the network stack.
It is. It temporarily buffers the packet, strips away the headers, and runs regular expressions regex against known threat databases.
It's actively looking for anomalous byte sequences.
Or protocol violations, or unauthorized command strings embedded within seemingly normal traffic.
And it can detect data leakage too, right?
Yeah.
By scanning for patterns that look like credit card numbers leaving the system.
Absolutely. And once it validates that the payload is clean, it reassembles the packet and passes it up to the application layer.
I mean, that is a massive computational lift.
It is.
But the source material makes it very clear that this ability to track connection states and run deep packet inspection locally is basically the primary weapon against the most devastating threat in the enterprise landscape right now.
Ransomware.
Ransomware.
Because ransomware relies almost entirely on the lateral movement we discussed earlier.
Right. An infection never just stays on one device if it can help it.
Exactly. A modern ransomware strain doesn't just encrypt the single laptop it initially compromises. It actively scans the local subnet, seeking out other vulnerable machines.
And it attempts to spread using protocols like server message block or SMB, right?
Yeah, which is typically used for file sharing. It also exploits remote services and administrative protocols like PowerShell remoting or the remote desktop protocol.
And this is where the host-based firewall basically creates a structural barrier.
Yes, the firewall drops unauthorized SMB traffic and restricts peer-to-peer communications between standard workstations.
So if an employee clicks a malicious link and a ransomware payload executes on their machine, the local firewall effectively isolates that process.
Right. When the malware attempts to establish an outbound SMB connection to infect the server rack down the hall, the local firewall rules intervene at the kernel level and drop the outbound packet.
It just starves the attack of oxygen.
That's a great way to put it. And on a larger architectural scale, enforcing these localized rules across the entire environment creates a framework called microsegmentation.
Microsegmentation. So you're dividing all your corporate systems into highly restricted, strictly enforced security zones. It's essentially like the bulkhead compartments of a submarine, isn't it?
Oh, I like that.
Yeah, like if you are underwater and one compartment gets breached, or in this context, compromised with a zero-day ransomware strain, the automated bulkhead doors immediately seal shut.
Right.
You might lose that one specific compartment, but you keep the rest of the submarine from flooding and sinking to the bottom of the ocean. So even if a hacker completely compromises my machine, the firewall literally locks that malware in a tiny room. It cannot spread to the server next door.
That is a highly accurate visualization.
Thanks.
And if we apply that to the enterprise examples from the guide, you might have a finance server handling sensitive transactional data.
Right. Yeah.
With microsegmentation enforced by host-based firewalls, that finance server is strictly configured to only accept incoming connections on specific ports from authorized accounting applications.
And the local firewall on the HR server ensures it only communicates with HR databases.
Exactly. And a development server used for testing code is absolutely barred from opening a socket connection with the production databases.
Period.
By enforcing these rules at the host level, you dramatically limit the blast radius of any successful breach.
I mean, that level of compartmentalization makes absolute sense from a security architecture perspective, but we do need to look at the operational reality here.
Yeah, the friction.
Because the source material doesn't shy away from the logistical friction this creates. Managing a host-based firewall on a single personal machine, pretty straightforward.
Sure.
But managing thousands or tens of thousands of distinct endpoints in a global enterprise introduces massive management complexity.
And user friction.
Right, because it sounds like a massive balancing act. How do organizations manage the tension between locking everything down to be totally safe and accidentally misconfiguring a rule that, say, blocks the CEO from giving an urgent remote presentation?
Well, if you set the public profile rules to be too restrictive, you end up with exactly that classic scenario. The CEO is sitting at an airport terminal, unable to reach a critical corporate server.
The network drops the connection, the software times out, and the executive is just stranded.
And when security protocols cause operational friction, users inherently try to bypass them.
Right, they'll find a way.
If they don't have strict administrative locks, users will simply disable the local firewall service out of frustration just to get their work done.
Which completely undermines the entire zero-trust architecture.
Yeah.
You can't rely on localized enforcement if the end user has the authority to just turn the enforcement engine off.
Exactly. And this is why enterprise host-based firewalls never operate in a vacuum. They are deployed as part of a comprehensive defense-in-depth strategy.
So they're integrated.
Highly integrated. To prevent misconfigurations and rogue users from disabling controls, organizations rely on centralized management platforms.
So security teams aren't configuring these endpoints individually.
No, not at all. They build, test, and validate policy sets centrally, and then push those configurations down to all remote machines simultaneously.
The source guide also highlights a significant ecosystem of integrations here. We see acronyms like EPP, EDR, XDR, and SIEM.
Right, alphabet soup.
Yeah, a lot of acronyms. But it points to a reality where the host-based firewall is essentially acting as the enforcement arm, but it's relying on other tools to provide behavioral intelligence.
That's right. The host firewall controls the network socket, but it integrates directly with the endpoint protection platform.
Which is the core antivirus engine.
Right. And it feeds telemetry to the EDR, the endpoint detection and response agent, which analyzes process behaviors and memory injection attempts.
And all that localized data has to go somewhere for analysis.
Which is where the SIEM comes in.
Right. Security information and event management platforms. Things like Microsoft Sentinel, Splunk, or IBM QRadar. They ingest the raw log data from every single host-based firewall across the entire global environment.
And by centralizing those logs, you gain correlation capabilities.
Okay, correlation.
Yeah. So if one isolated laptop drops a suspicious connection attempt on an obscure port, it might just be an anomaly.
Sure.
But if the SIEM correlates log data showing that 40 different laptops across 3 different geographic regions are all suddenly blocking unauthorized PowerShell remoting attempts at the exact same millisecond.
The Security Operations Center knows they are dealing with a coordinated attack.
Exactly. And they can automate a response.
And that level of comprehensive logging isn't just a technical advantage, it's often a regulatory requirement, isn't it?
Oh, absolutely. Organizations handling payment processing are subject to PCI DSS audits.
And companies managing healthcare data or sensitive intellectual property fall under NIST frameworks, SOC, or ISO 27001 compliance standards.
And the auditors for those frameworks require cryptographic proof that these endpoint controls are actively managed, logging connection attempts, and taking a default deny approach.
Default deny.
Yes. The default deny approach is basically the cornerstone of zero trust. Unless a specific application on a specific port initiated by an authorized user is explicitly granted permission to communicate,
The firewall just silently drops the traffic.
you never assume trust based on the network connection. You verify every single request continuously.
Well, this deep dive really highlights the massive evolutionary leap in system architecture we've seen.
It really does.
I mean, we looked at the inherent vulnerabilities of the old castle and moat perimeter, recognizing that as remote work and cloud infrastructure expanded, edge defenses just became insufficient.
They failed completely.
Yeah. And we examined how the enterprise shifted the protective layer directly to the operating system using host-based firewalls.
Right.
We walked through the deep mechanics of stateful inspection, monitoring TCP handshakes in active memory, and deep packet inspection, tearing down payloads to run real-time pattern matching.
And we saw how utilizing those localized enforcement rules to build microsegmented zones creates the ultimate containment strategy against lateral movement and ransomware propagation.
All while feeding critical telemetry back into centralized SIEM platforms for global threat correlation.
Exactly.
So for you, the listener, understanding these mechanisms really bridges the gap between abstract security policies and the everyday reality of your digital life.
Because your laptop, your mobile device, your virtual environments, these are the active front lines now.
They are. Recognizing how this silent software engine analyzes network contexts, evaluates states, and drops malicious payloads helps clarify exactly why your data stays secure when you're navigating untrusted networks.
It really puts it into perspective.
It does. Before we go, we want to remind you to please follow the channel so you never miss an analysis of these critical systems.
Yeah, hit that follow button.
And be sure to visit WeCyberYou.com for more content like that, where we have an entire library of technical breakdowns waiting for you.
And I actually want to leave you with a final thought to mull over as you close out this session.
Ooh, okay.
We've explored the incredible technical depth of these localized defenses today. But if our individual endpoints are becoming so highly capable of defending themselves dynamically,
Like running complex deep packet inspection and actively blocking lateral movement.
right, if they're enforcing strict zero-trust rules without relying on a centralized gateway, will the very concept of a shared corporate network eventually become obsolete?
Yeah.
Are we moving toward a future architecture where networks are entirely untrusted transport layers, and we exist simply as a sea of completely isolated self-defending endpoints?
Man, that completely flips the traditional security model on its head. If the individual bulkhead compartments are indestructible, you might not even need the submarine anymore.
Something to think about.
Definitely. Well, thanks for joining us on this deep dive. Stay curious, stay secure, and we will catch you next time on the WeCyberYou Unlocked podcast.